In this section, we'll talk about propositional equivalencies. First, we'll look at the tautology definition. A compound proposition that is always true, no matter the truth values of the propositional variables that occur in it, is called a tautology. A compound proposition that is always false is called a contradiction. A compound proposition that is neither a tautology nor a contradiction is called a contingency. We can look at a simple example of a tautology and of a contradiction and put those into a truth table. So let's start with P and not P as our two propositions. And we can look at P or not P. And then last we'll look at P and not P. So we'll fill out the truth table, true, false as our potential values for P. Then the negation of that is false and true. And when we have P or not P, we have true, false. And with an or, that will result in true. Then we have false and true, which results in a true with an or. Then in our, so that is our tautology, because this is always true. So that is tautology. And then we'll look at our P and not P. And there we have true and false, gives us false. And then false and true gives us false, which means that this is a contradiction. So your tautology is a compound statement that always results in true, and a contradiction is a compound statement that always results in false. Next, we'll look at what it is to be logically equivalent. The compound propositions P and Q are logically equivalent if P, if and only if Q, is a tautology. The notation P is logically equivalent to Q using the three-line equal sign denotes that P and Q are logically equivalent. Next, we'll look at an example. Show that the negation of the quantity P and Q is logically equivalent to the negation of P or the negation of Q. To do this, we'll set up a truth table. So I'll put P and Q. And in the next one, I will do P and Q, so that following that, I can do the negation of P and Q. And after that, I'll do the negation of P, and I'll do the negation of Q, so that I can do the negation of P or the negation of Q. Alright, so we'll start by filling out my truth table. True, true, false, false for P. For Q goes true, false, false. And then for P and Q, I have true, true, which is true. True, false, which is false. False, true is false. And false, false is false. Then the negation of that, the true goes to false, the false goes to true, false goes to true, and false goes to true. Then I have the negation of P, so true becomes false, true becomes false, false becomes true, and false becomes true. The negation of Q, true becomes false, false becomes true, true becomes false, and false becomes true. Now I have the negation of P or the negation of Q. So I have false or false, and that is false. I have false or true, that is true. True or false is true. and true is true. So once I have these, I can see this and this are these columns here, and those two columns have the same truth value, therefore they are logically equivalent. That is, and that is. And as it turns out, what we just did was we showed this is one of De Morgan's laws. And we just showed that it was true. Next, we'll look at another example to show logical equivalency. This time, we'll show logical equivalence between the negation of the quantity P or Q, and show that's logically equivalent to the negation of P and the negation of Q. And this is another one of De Morgan's laws. Again, we'll set this up in a truth table. So we'll put P and Q. Then we'll do P or Q. Then we'll do the negation of P or Q. Then we'll do not P, not Q. And then we'll do not P and not Q. So we'll start off with a truth value for P, true, true, false, false, and Q, which is true, false, true, false. Then we have P or Q, true, true is true. We have true or false, which is true. False or true is true. False or false is false. The negation of that becomes false, 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 true. The negation of P is false, false, true, true. Negation of Q is false, true, false, true. And when we take the negation of P and the negation of Q, we get false and false is false. We get false and true is false. True and false is false. True and true, that is true. Now we can look and see that this column has the same truth value as this column, meaning that those two are logically equivalent. So we just showed that the other De Morgan's law is true. Next, we'll look at the associative law, which holds true for disjunctions and conjunctions. In this example, we'll look at the associative law for disjunctions. So we have quantity P or Q, and quantity or R is logically equivalent to P or quantity Q or R. And to do this, we'll look at a truth table. And unfortunately, this is going to be a long truth table because we have three variables. So let's go ahead and set these variables up. True, 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 true. False, 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 false. And we know there are going to be 8 potential combinations. So we start the P, true for the first 4, false for the second 4. And then we cut the 4 and 4 in half on the next one for Q. So Q is true, true, false, false, true, true, false, false. And then we cut that number in half again. So we cut the 2 in half down to 1. So now for R, it alternates every variable. So true, false, true, false, true, false, true, false. And that gives us all of the possible combinations. And then we need to come up with P or Q as our next piece that we need to solve. So when we're doing P or Q, that's true or true is true. True or true is true. True or false is true. True or false is true. False or true is true. False or true is true. False or false is false. And false or false is false. Then we need to combine that result, the P or Q result, with or R. And that's our next column. So now we're comparing this one and this one. And that will give me true or true is true. False or true is true. True or true is true. False or true is true. True or true is true. False or true is true. True or false is true. False or false is false. Then we need to go about this the other way, and we need to do Q or R first. After that, we'll be able to do P or that answer of Q or R. Okay, so now we're doing Q or R. So that gives us Q or R. Let's go with a different color here. So for Q or R here, we're going to take Q, compare that with R. I'll just draw the colored arrows out there so that it's easy to keep track of what we're doing here. Okay, so true or true is true. True or false is true. False or true is true. False or false is false. Then true or true is true. True or false is true. False or true is true. And false or false is false. Then next column, we need to combine the Q or R with P. So when we combine that, we get true or true is true. True or true is true. True or true is true. True or false is true. False or true is true. False or true is true. False or true is true. And false or false is false. And if we look at that, that means that this column and this column have the same truth values, therefore they are logically equivalent. And we'll leave it up to you to prove the other one for a disjunction, since they're so long. Next, we'll look at the distributive laws, which are both listed here. And to start with, we will just look at this one, the first one. Again, just because of the number of variables here and how long the truth table gets, we'll just look at one of them and leave it up to you to perform the proof for the other. So, scroll this up just a little bit. We'll set up the truth table. We've got P, Q, and R. So we've got true, 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 false, 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 false. And then we've got true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. And then let's take a look at the Q and R as our first thing that we'll examine. True and true is true. True and false is false. True and false is false. False and false is false. True and true is true. True and false is false. True and true is true. True and false is false. Then we'll combine that with the P. So we go P or Q and R. So that means we've got true. Got true or true is true. True or false is true. True or false is true. True or false is true. False or true is true. False or false is false. False or true is true. And false or false is false. Then we need to look at excuse me. So next we need to look at P or Q. Then we'll look at P or R. And then finally we'll look at P or Q quantity and P or R quantity. Okay, so for the P or Q is true or true, true. And true or true, true. True or false, true. True or false, true. False, true. It's true. False or true is true. False or true is true. And false or true is true. Then we've got P or R. P or R is true or true is true. True or false is true. True or true is true. True or false is true. False or true is true. False or false is false. False or true is true, and false or false is false. Then we have those two last columns combined together with an and. So true and true is true. True and true is true. True and true. True and true is true. True and true is true. True and false is false. True and true is true. And true is false. So that means we've got this column here and this column here. And if we look at those line by line, they have the same truth values. Therefore, this is logically equivalent to this. Therefore, we've shown that our distributive law holds for that. And as I said before, I'll leave the second one to you to prove in your own truth table. There are several other simpler logical equivalency laws that are important, and I'll leave those to you to verify with truth tables. Those are the identity laws, domination laws, double negation laws, absorption laws, and negation laws.